Welcome everybody to the ninth lecture from the Summer School on Dynamically Deformed Solids, sponsored by CREDDS. Today we're glad to welcome Dan Dolan from Sandia National Laboratory, who will be telling us about diagnostics of dynamically deformed solids by optical velocimetry. Dan is a technical staff member, as I said, at Sandia. He received his PhD in 2003 from Washington State University. I'll modify that in a minute. His interests are in shock physics and diagnostics. So thank you very much for joining us, and I will hand over the screen to you now.
Okay. Let's see, is that showing up?
Yep.
Can people see that? All right. Well, thank you. It's a nice opportunity to be able to talk to lots of different people, especially students. This is something that's interest to me, but it's really sort of at the heart of experimental shockwave physics, and that's optical velocimetry. As I said, my name is Dan Dolan. I'm in the Dynamic Material Properties group at Sandia National Lab. One of the many things we do is experiments on the Z machine. Many of you have probably seen this very, very famous picture of the arcs and sparks, and we use that to generate massive amounts of deformation and compression in solid materials. So the overview of this talk is as follows. We're going to have some background about why we measure velocity in the first place, and then talk a little bit about transit time measurements, which were sort of traditional ways of doing shock physics. Then we're going to switch over to optical Doppler shift measurements, and that sort of falls into what we call displacement interferometry and velocity interferometry, mostly what we're going to talk about when it's known as VISAR, a very famous technique that some of the previous lectures have mentioned. I will then transition into photonic Doppler velocimetry, or PDV, which has sort of taken storm in the last 20 years or so. Some technology overview, a bit of the theory, and then quite a few examples of how PDV is used in the study of dynamic compression. So why do we measure velocity? Why is it sort of the core diagnostic for almost every experiment? Well, it's because something we can measure. And not only can we measure it, we can measure it with very fast time resolution. These days, we can do nanosecond or better. We can also measure with very high accuracy, 1% or often better accuracy. Velocity is something you can measure in extremely harsh conditions, plate impact, detonation, intense laser pulses or electrical discharges. It's something that we are able to measure regardless of what's going on around. We can do it lots of places simultaneously. And sort of one of the big drivers for velocity is it's something you can directly compare to wave codes. It doesn't matter if you're an Allegro person or a CTH. Any wave code is going to have a way to track velocity, and so you can directly compare a measurement you make with a simulation that you did. Even more basic than that is that the pressure and density are linked to velocity in terms of the jump conditions. I think Bill Anderson covered this a few weeks ago, that the density ratio ahead of the shock front versus behind the shock front was related to the shock speed divided by the shock speed minus the particle velocity. So if you measure those two things, you immediately know how much the density has changed in a one-dimensional shock system. You can also immediately calculate the pressure from particle velocity and shock velocity. And what you find is that most tabulated data on materials, this particular page, I just took a snapshot from the Los Alamos shock tables on iron. You see things like this. And really what was done is that people measured particle velocity and shock velocity, these two columns, and that's this plot. And then from that, they calculated pressure and density, in this case, specific volume, which is 1/density. These are calculated from those measurements. It's a little confusing because they show it as if density is the first column, but really density is derived from something like this. And so the heart of high pressure physics, dynamic compression, is really velocity measurements. Now, in the old days, what we would typically do is have some sort of experiment where you would load a plate. This could be impact, but a lot of the experiments, particularly Los Alamos, were explosively driven. And you create a shock in this drive plate, and behind the drive plate you have samples of interest. So the plate might be something we'll characterize, and then this would be something that you're interested in studying. You might have different samples, different thicknesses. The shock wave would sweep the samples and break out on the free surface, and also break out here on the drive plate. And so what people would do is either put an electrical pin very, very close to the surface so that when the surface began to move, it would close the pin, and then you measure something happened. A lot of the technique is they would have very thin gaps of argon that were placed right behind the target. And so when the shock came by, it would squeeze the argon, it would get very hot, begin to glow, and so you could there was a clear optical signature of breakout. And then basically, if you knew when something broke out before the sample and on the back of the sample, and you knew the thickness of the sample, you would measure your shock speed just from the transit time, delta t, and knowing the original thickness. You're halfway there now. You've got US, and if you knew something about the drive plate, you could infer particle velocity, and then you've got your table point. So an enormous amount of data in the literature is derived from this type of experiment. Now, the way those experiments were made is kind of interesting because if you think about how fast you can record something, in the late 40s, 50s, things were sort of limited electronically. So you'd use these rotating mirror street cameras. And the way this works is that light from the sample, so if your argon flashes are happening over here, would be directed at this rotating mirror. The mirror would divert that light onto a drum of film. If you then process the film and looked at the exposures, you could say, well, one set of light started here, and then on the thicker piece, it was here, and this distance was your transit time. And again, so a huge amount of tabulated data was done exactly like this. Of course, you do have to know the rotation speed very, very well, and film distortion can be a problem. These days, most people don't use rotating mirrors. There are streak tubes, which do this more electronically. And but the old system allowed you to get sort of 100 megahertz bandwidth recording. Now we're into the multi-gigahertz, particularly in laser facilities using streak tubes. Now, over time, oscilloscopes got to be faster, became faster and faster, and you saw less of this kind of measurement. As I said, in the late 40s, so a little after the Second World War through this 1960, you had sort of tens of megahertz of bandwidth from an oscilloscope. Around 1960, you got your first gigahertz class oscilloscope, but then the technology sort of saturated and transitioned from an oscilloscope, which had an electron beam on a tube, to more of a digitizer, which some of the younger people probably may have never seen old-fashioned oscilloscopes. In the mid to late 90s, you started to get gigahertz and higher class digitizers. These days, you can get tens of gigahertz, and this plays into why we do things a certain way later on velocimetry, what the limitations were that drove certain decisions. Now, if you were very clever, you could do things with pins that maybe at first you think would be impossible. So back in the mid-50s, at Los Alamos, a bunch of people started putting iron. They started studying iron, which has a phase transition. And so in order to resolve that phase transition, this is an explosive shock here, where you have a shock wave coming through, hitting this target plate, and then they put lots and lots and lots of pins at different distances. Here's a cross-section. I think I count 59 pins in the middle, 10 pins on the outside, for sort of tilt and time of arrival. And then you just record, when did pin 1 short, when did pin 2 short, when did pin 3 short. From that, you can make these plots of arrival time versus distance from the free surface. And they notice are these breaks and slopes. And so if you put those all together, you realize that, oh yes, here is the phase transition in iron. There's, above the transition, or below the transition, above the transition. You wouldn't be able to get this from a simple transit time measurement. By doing lots and lots of small measurements, you can sort of tease out these features. But to be honest, most of us, including myself, are not that clever, and this is very difficult to do, and wasn't done for very many materials because it's an enormous amount of work. What you really need is a way to study non-steady waves. I mean, what I think the past few weeks people have been talking about, when you apply a load to a sample, what comes out of the back tells you something about the material. And it's not always a simple shock. I mean, oftentimes if you have, say, an inelastic compression, there are structures. So this is sort of your stereotypical, there's sort of a precursor, a relaxation, and then a plastic wave behind it. Well, this sort of thing is hard to resolve with pins. The same thing is true of phase transitions, chemical reactions, or even the fact of maybe you don't drive the shock waves. Maybe this is a release wave. I think Bill Anderson had pointed this out some weeks ago, that release waves tend to ramp out. They're not steady shocks. You can also tailor the wave using, I said, laser drive or electromagnetic drives. There's no reason this can't be a continuous pressure wave instead of just a shock. All of those things are very hard to get out of a transit time measurement. So you really want something real time where I can infer the velocity at this point, this sort of Lagrangian location, at all times. And that's really what the heart of this discussion today is about. So we're going to discuss optical velocimetry, and there's lots of ways you can track motion with light. I mean, the simplest we've already talked about, that's optical emission. Your shock creates light. So that's basically the example of that would be the argon flash gap that Los Alamos sort of used at the beginning of the shock physics program. Sometimes you see that as called passive shock breakout. It's passive because you as the observer don't have to do anything. The sample emits its own light. There's also all kinds of reflection techniques that either look for a change of amplitude or change in direction. So that's usually called active shock breakout because you have to send light to the target. Sometimes that's based on a change of reflectant, just the amount of power that comes back. Sometimes it's directional. The Russian shock physics program back in the 60s was really great at this, but it does require some very special geometry, and you have to have specular surfaces to bounce a beam off. So the idea of, imagine pointing a laser pointer at your bathroom mirror that you can open and rotate. That's essentially what deflection is. But most of your more flexible techniques are based on optical phase. And so optical phase, if you remember from your sort of undergraduate physics courses, light is an electromagnetic wave, and the field, if you think about just the electric field, is sinusoidal, and the thing that's inside the cosine function that's what we mean by phase. It's the thing that wags the field up and down. The frequency is the rate of that phase change. You can sort of show that that's proportional. So phi, be my phase, is proportional to the optical frequency, and there's some 2 pi's to go from radians to frequency. Wavelength is just the reciprocal of frequency. So you take the speed of light and divide by wavelength, you get frequency. Sort of a common example is 532 nanometer light, which happens to be the frequency that's the light that's used most commonly in VISAR, is 564 terahertz. What that means is that the electric field in that beam flips over every 1 or 2 femtoseconds. So these are the fields flip over very quickly. We don't usually measure the field directly. We usually think about things like wavelength. And so if you remember your Doppler effect, there's a classical Doppler effect for sound, but there's also an optical a Doppler effect where me sitting in the lab looking at a laser with the wavelength lambda, if I shine that onto a moving reflector, the reflector sees a different wavelength because of a translation from one reference frame to another. They see a somewhat different wavelength, lambda prime. When the reflector bounces that beam back at me, there's another transformation, and I see yet a different wavelength, lambda. You can show that these wavelengths are related by 1 minus twice the velocity over the speed of light. This is an approximation, but it's a pretty good one because even at 100 kilometers per second, you're only 0.03% the speed of light. So most experiments, even high-speed shock measurements, are very much non-relativistic. And you basically pick up 2 Doppler shifts, if you want to think about it. One going from the rest frame to the moving frame, and one going from the moving frame back. You get a very small change in the wavelength. Now, when you say optical velocimetry, what you usually really mean is optical interferometry, because we can't measure the field. The electric field flips over many, many times faster than even the fastest optical detector when you're talking visible or even infrared light. So that's out. You can't measure field. You also can't really detect wavelength with any kind of dispersive spectrometer. So I mean things like gratings or prisms, because the shifts are so small. If you imagine a motion of 1 kilometer per second, gives you about 6 or 7 part per million change in the wavelength. So that's like measuring 4 picometers at 532 nanometers, which is well below the resolution of virtually any dispersive spectrometer. What you end up having to do is some kind of interferometry, and the most common approach is a 2-beam interferometer, where you split light along 2 different paths, you mix those lights, those signals, and you get something that looks like this. It's an interference equation where I represents optical intensity, that's power per unit area. The electric fields themselves add coherently, but then when you look at the intensity, you actually consider the time average square of the electric field, and you get something where the cosine here has the differences in optical phases. So although I can't measure optical phase directly, I can measure the difference between phases very accurately. So just some general terminology before we go on is that when people talk about fringe shift, what they just mean is a phase difference scaled by 2 pi. So if I imagine some sort of signal like this, and I went from peak to peak, or minimum to minimum, that's 1 fringe or 2 pi phase. It's the same as signal cycles. The beat or fringe frequency is how quickly these cycles are coming. It's not the same as the optical frequency. So sometimes we have to be careful we're not confusing topics, that we can only measure signal cosines. That is, a detector puts out so many volts, or that you measure on an oscilloscope or a digitizer, but we can't measure the electric field cosine directly because that's the femtosecond type of time resolution. So I want to take a brief historical detour on something that Lynn Barker invented at Sandia here back in the, I'd say it was sort of the late 60s. This is just the references in the 70s, called the Sandia displacement interferometer. And this is sort of the most obvious approach people would choose if you had any physics background and you wanted to track motion with a light. You'd say, okay, I've got this laser. I'm going to shine the laser at a beam splitter. Half the light from the beam splitter will go to my target, which is moving. The other half will go to a stationary mirror, which is not. So the light that comes back from each of these, again, goes to the beam splitter and gets mixed. I'll put that on a detector. And I know, and in fact, some of you probably have done this lab, that every time the specimen moves by half a wavelength, I get one fringe. That is to say, the optical signal goes through a full cycle, a minimum and maximum type of cycle every time. And on the bench, you can set this up and get extraordinarily high resolution displacement measurements. But there are a number of problems that kept this from ever being used in practice. The first thing is that this surface has to be polished to a mirror finish, which is actually shown here in the diagram. But in shock physics, it's very hard to preserve that kind of polish, particularly on a free surface. Usually you get little microjets or ejecta or all kinds of junk comes off of here, and then you immediately lose your measurement right at the time you wanted it, you were most interested in it. The other problem is just the limited velocity range. So if you work this out, if half a wavelength is a fringe, 1 kilometer per second is the signal of 3.2 gigahertz. That is to say, your electrical signals need to be that fast if you're using a helium neon laser, which I believe is what Barker had at the time. Well, there was no way to record that kind of high frequency information in the 1970s. So although these interferometers did exist in dynamic experiments, they were limited to very, very slow measurements. So this takes us to VISAR, which stands for Velocity Interferometer System for Any Reflector. And the VISAR solves this bandwidth problem with an interesting twist. So instead of mixing Doppler-shifted light with a stationary reference, you mix Doppler-shifted light with a time-shifted version of itself. So I'm going to go through the part that's in dashed red here is the actual VISAR. Everything outside of this is just light delivery to and from the target. But the point is you're bouncing a laser off a moving projectile, in this case, or target. You're getting it into the VISAR. In the VISAR, you polarize the light so that the electric field is moving in one direction only. You pick off some of that light and you monitor it so we can later on to tell the difference between light power variations versus interference variations. The rest of the light goes into this interferometer cavity where, again, there's a beam splitter. One side of the beam splitter has an etalon in it, and so you're able to mix light along two different paths. There's a quarter wave plate in here which takes your linear polarization and makes it two orthogonal polarizations, S and P. Those get recorded. And this avoids large steady state frequencies. So even if the target is moving at high speed, but if its speed isn't changing, we can get measurable signals here in a way that the displacement interferometer could not. And the use of this etalon allows diffuse reflectors, that this does not have to be a perfect mirror. You can still get usable fringes. Here's an example where Barker and Hollenbach applied the VISAR to iron again. So instead of having all the pins like was done in the 50s, you could in real time see the elastic precursor, the plastic, sort of a plastic wave, and releases. This kind of structure falls out in a single measurement rather than having to have hundreds and hundreds of pins. So what is the difference between those two? Well, in the displacement approach, you had light that was, get this out of the way. You had light that was going to the target. You pick some of it off, and it never touched the target. You mix the light that comes back from the target that's Doppler shifted with that signal. So fundamentally, there are two different optical frequencies, one with a Doppler shift and one without the Doppler shift. That's the displacement approach. The velocity approach, you send all your light to the target, and what comes back gets split. So you split post-target, not pre-target. And so both output paths contain the Doppler shift, and you're basically mixing two copies of a single frequency, a single optical frequency, I should say, with one little caveat, one little legal disclaimer, which we call the Weisar approximation. The Weisar approximation says that, look, if your velocity is not changing very quickly, or at least not quickly over the delay time of that etalon, remember the etalon is this chunk of glass here. This really is just a slab of a delay bar. If it's changing slowly compared to that delay, you can show that the fringe shift is proportional to the velocity by this series of parameters, where lambda naught is your wavelength and tau is the delay through the etalon. Basically, yeah, so that's called the Weisar approximation. The exact behavior is more complex. If you're interested, you can look in the Journal of Dynamic Behavior Materials for a frequency domain approach to this. But the vast majority of all Weisar measurements, you assume this holds. And then what this means is that you've got a sensitivity, or VPF, or fringe constant, those are all the same terms, that says how much fringe shift do I get for so much velocity, or how much velocity per fringe shift? Well, that's lambda naught over 2 tau. Tau, the delay time, sort of ranges between a tenth of a nanosecond to about 10 nanoseconds, which corresponds in the visible light from 50 meters per second to 5,000 meters per second per fringe. So what that means is that if I have, say, 1 kilometer per second velocity change, and I have 100 meters per second per fringe, I'm going to get 10 fringes. That is 10 optical cycles out of that Weisar. These are sort of physical limits. To go smaller than a tenth of a nanometer is hard, or excuse me, tenth of a nanosecond. It's hard to characterize. To go greater than 10 nanosecond is just very hard to build. A lot of glass, and it becomes tricky to make. So most Weisar measurements use quadrature, and quadrature just means you have these two signals that are out of phase. Remember, I mentioned that there were two optical polarizations. The reason you want to measure these two states is that inverting a sinusoid can be very tricky. I mean, if I just give you a sine function, sine wave, and said invert it, well, the arc sine and arc cosine are only defined over 180 degrees. So that's one problem. And what you also find is that if you happen to be operating in a part of the signal that's steep, that is to say a small amount of phase shift gives you a large signal change, that's great. But if you're near the peaks and the troughs, you're very insensitive to changes. So by having two phases, it turns out that no matter where you are, there's always some sensitivity. Plus, I can roll these two together. So if I take the blue signal, put that on the x-axis, and I take the green signal, put it on the y-axis, I trace out a Lestadiou pattern, ideally a perfect circle, where I can robustly invert phase no matter where I am on the circle. And of course, the arc, if you use the correct arc tangent, it is defined over a full 360 degrees instead of 180 degrees. So let's go through an example of how a Weisar senses, let's say in this case, a ramp velocity where I start at rest, and over 200 nanoseconds, I uniformly accelerate until I get to here. Okay, so these circles indicate a starting point. So I have my two signals when I'm here. As the velocity changes, I start seeing these fringes. So I get these oscillations until I stop moving, or should I say stop accelerating. So up here I have steady velocity. Again, I have steady signals. The only time the signals are changing is when the velocity is changing, and that's where the term velocity interferometer comes from. If you want to think about where you are on a Lestadiou pattern, here's your circle. That's your starting point here. As you move around the circle, you get to here, which is the squares here. And you got your upward triangles and your downward triangles, and then your asterisks. So you're just kind of moving around the ellipse. And as long as you can keep track of where on the ellipse, you can figure out what the phase shift, or how many fringes. Every full trip around is one fringe, which is one fringe shift, one VPF of velocity. Now it gets a little tricky. Here's the same type of motion where the acceleration is just over, it's a shock with the same delay time. So I instantly transition from here to here. Well, the problem is if I have a finite bandwidth in my detectors, I see something like this, and then when I plot it, I'm like, well, wait a minute. It looks like I go backwards. Instead of going around this way, I just jump back that way. The problem is that optically, all the fringes that you see here still appear here, but if your detector can't keep up with them, they're lost, and there's some missing information here. That's one of the cold hard realities of VISAR, is that first of all, you only know fringe shift to an integer offset. I mean, because any cosine of a value is equal to cosine of that value plus 2 pi plus 4 pi and so forth. If you can't keep up with the signals, which is what happens here, so all these signals, all these oscillations optically are happening, but the detector can't resolve them, it misses the fact that you went around, and so you jump a fringe. People talk about losing fringes, jumping fringes. That's essentially what's happened, is that you know where you're on the ellipse, but you've lost how many wraps you might have had. To resolve this, you typically have dual VPF, where one or more VISARs looking at the same velocity. So if I have the velocity I'm measuring, if I've got one VPF and one fringe shift, so F1 is measured, and a second VPF and a second fringe often measured, I have to be able to add integers and get a consistent number, a consistent result. And that can be tricky depending on how your VISAR is set up, but that's how it's normally done, is you almost always run VISAR with at least 2 VPFs instead of 1. Another problem is that VISAR is designed really to measure one fringe shift from a single Doppler shift. That is to say, I've got a target who's allowed to accelerate, but there's only one velocity in the field of view always. If you start getting multiple velocities, what happens is that instead of moving around the ellipse, you kind of spiral into the center, and you lose all your coherence altogether. And so that's a long-standing problem with the VISAR. A tricky thing is that the ellipse position and the size change with the light level. So if your return is getting brighter or weaker, all of this is moving around. You're not only going around this, but the whole circle is itself moving, which is kind of fun. So over time, there have been some improvements to VISAR to address these issues. One of them was the development of the push-pull quadrature. So in Wilhelmsen at Los Alamos modified the VISAR. So instead of just measuring two signals that are 0, 90 degrees, you measure 0, 90 degrees, 180 degrees, 270. So there's 4 recorded measurements. And if you put these together correctly, you can remove a lot of the light variations and have a very robust measurement. Another big change is fiber coupling. Originally, VISAR was an open beam diagnostic. You had, sometimes these lethal death rays of light bouncing around the lab. These days, we don't generally have open beam VISAR unless it is a line VISAR measurement. That's a spatially resolved version that you still see in a lot of laser shock experiments. There are faster detectors. We could always streak a VISAR measurement instead of using photodiodes, photomultipliers. That's often called an Orvis. There have been some improvements to photodiodes and photodetectors, and there are faster digitizers. Most of this has been incremental for the last 2 decades. I mean, if you showed somebody your VISAR, if you took a technician from 1990 and showed them your current VISAR, they probably wouldn't be very surprised by anything other than maybe the software controlling the CCD. Everything else is more or less the same than it has been. So let's transition now to PDV, or photonic Doppler velocimetry. PDV was really born in Livermore. It was really closer to the year 2000, but people didn't start talking about it until 2002, 2003. And one of the key things of PDV is that it's based on telecommunication equipment, things that are 1550 nanometers and thereabouts. There's a host of technical developments that we, even the national labs, could never have afforded to make on our own, but billions and billions of dollars are put into telecom to make these devices. So first of all, you have these compact fiber lasers. They operate at this wavelength, and they use single mode fiber. So, your glass in an optical fiber is like 125 microns in diameter, about the width of a human hair. Inside of that, there's a 9-micron core where you confine the laser beam in a single mode. These are sort of commercial devices that you can then split out across many, many probes. And they're extraordinarily stable. They have very narrow line widths optically. They also developed these, what they're called 3-port circulators. These are a fiber device where magically light that you send in the input port 1 comes out of port 2, and anything that comes into port 2 goes out of port 3 with very little leakage from 1 to 3 or from 2 to 1. And again, this development, it sounds conceptually simple, but there have been many, many, many man hours and billions of dollars developing these. Now we just buy them, and they're maybe the size of a pencil with some fiber sticking out of it. So in a PDV, you send light through the circulator out to a probe. In the original generation of PDV, some light in the probe some light would be reflecting the probe before it went out to the target. The rest would go at the target, get Doppler shifted, and then both signals were mixed on that input. and they'd come out port 3 to an attenuator, power monitor, and there are these high-speed detectors and digitizers, once again driven by telecom, with bandwidths in excess of 10 gigahertz. Putting these all together, Ted Strand made a very workable PDB. Said it was only documented in 2006, but he'd been tinkering with this for at least 5 years since then. So this is sort of the heart of PDB. There is a very recent comprehensive review article that came out in Review of Scientific Instruments if you want to know more, but I'm going to go through some of the detail highlights here today. So the way a PDB works is it's basically a Michelson interferometer. Now half a wavelength is 775 nanometers at 1550. That gives you one fringe. So if I have my ramp looking like this, my signal is flat when I'm at rest, and then as I move, the faster I move, the faster I get fringes. So really, we're back to the displacement interferometer that Lynn Barker had tried to build in the late 60s and the early 70s, but it's all in fiber. So the derivative, the rate of change of the fringes, which is equal to the beat frequency, is just twice the velocity divided by the wavelength of light. Now, there are many names for and configurations of PDB, which makes life very, very confusing. I mean, there's your conventional, I consider this Lynn Barker's, the conventional PDB. There are some minor variations on this, but if there's one laser and you're measuring frequency, it's a conventional PDB. So there's just one laser wavelength. It is confusingly called heterodyne velocimetry, even though there's only one laser. I won't get into what's heterodyne, homodyne, but you do see sometimes it's called HET-V, particularly in the United Kingdom. They call it HET-V instead of PDB. Then there's a whole subset of PDB that's based on quadrature. There are ways of obtaining quadrature signals. Instead of 90 degrees, they're 120 degrees out of phase. Sometimes it's called triature, sometimes it's called PDI, DISAR. They're their own class of measurements, which I'm only going to briefly touch on today. Most measurements these days are what I call frequency-shifted PDB. In that case, there's two laser wavelengths, or there's a laser plus a shifter. So in the two laser approach, one laser goes to the circulator, hits the target, picks up the Doppler shift, and then that Doppler shift is mixed with a second laser altogether. So these two are usually independent of one another. Then you tune the wavelengths to give you the beat frequency you want. A related version is that you do still split a single laser, but then you go through an acousto-optic frequency shifter. So you again are having two wavelengths there. The benefit of this is that you can use a less stable laser because if its wavelength drifts, both legs are drifting together. This requires better lasers. However, the AO shifters are also fixed. If you want a 500 megahertz shift, you buy a 500 megahertz shifter, and that's what you have. The lasers are much more infinitely tunable, but perhaps less stable. So here's an example of a step measurement that is like a shock breakout where I was at rest and I instantaneously jump to a final state. Well, in a conventional PDB, if there's no motion, there's no fringes. I have flat signals, and then when I jump up, I get this oscillation. Remember, the density of these fringes depends on the wavelength and how fast I went. But in frequency-shifted PDB, you can set up your lasers such that you're always fringing. I had a certain frequency here, and then on breakout, I had a different frequency. And this is actually very helpful when you're setting up your digitizer because then you have something to look at. You know what to set your vertical sensitivities to. Whereas in conventional PDB, people are trying to flick fibers to get a little bit of fringing. It's not always very consistent. If you've been doing frequency-shifted PDB, you often find conventional PDB hard to deal with because of that. So let's think about how velocity maps to beat frequency. And the point of frequency shifting is to change that mapping. In a conventional PDB, if your velocity is 0, your beat frequency is 0. And as the velocity increases, the beat frequency increases to something like this. The dashed line indicates sort of the bandwidth of the system where I can't measure beyond that. So that's my fastest velocity. And then this lower dotted line has to do with how fast do my frequency have to be able to get a full cycle in the time I'm interested in. So we have problems with low velocity down here. In an upshifted measurement, what you do is I have a reference laser that's longer than my target laser wavelength. That boosts you up here so that even when the velocity is 0, I am beating. As the velocity increases, my beat frequencies increase, and that's what I was showing in this plot here. What's kind of cool is then if your beat frequency starts going down, that means I'm going the other direction, which I haven't shown here, but it would just be the projection downward. Now, it is also possible, instead of upshifting, you can downshift. So now you make a reference wavelength shorter than your target wavelength. And what'll happen is you can start up here and initially have beat frequency decrease with velocity until what happens is if the Doppler shift exactly matches the difference between the lasers, then things turn around. We call this a bounce. You get something like that. The reason I show this is that it turns out the mapping between frequency and apparent velocity isn't unique. There's always, every beat frequency has two apparent velocities that could satisfy it. I mean, some of them over here on the negative side, and using physical principles, sometimes you can reject those and say, well, I know my target is moving towards me, not away from me, so I'll skip this. But on this side, if I just told you the frequency was here and I'm on the orange curve, is it this velocity or is it this velocity? So sometimes we use what's called leapfrog PDD. That's where I have two downshifted measurements, and I kind of hop back and forth between them to avoid areas of problem. So I avoid this region down here, I avoid it here, I also avoid the bandwidth limits there. So I can expand my coverage and get unambiguous interpretation. Mathematically, this is the expression that always applies, that the velocity sits inside of this absolute value signal scaled by 2 over the wavelength. These are optical frequencies, and there's the beat frequency. I can only measure positive beat frequencies, and so that's where I get these bounces from, is that absolute value sign. I'm going to go through a more complicated example. The first one uses what we call quadrature PDD. So that's where we have signals that have 120-degree phase shift. And so when I am at rest, those signals are constant. And then as I accelerate, I get this fringing, and it looks something like this. When you analyze these, you have to unroll the phase, and then you take a derivative of that phase to get frequency. And a frequency shifted signal, this is what you see. And it's not much to look at by the eye. I mean, if you're looking at it, you might say, well, I can kind of tell it's less dense here than it is here, but I don't see any details. However, it's very obvious if you do a spectrogram, that is a time frequency analysis of this, you can get these spectra that look like this, and then it's very clear what's going on. And this is actually derived from that. This all sort of hinges on what we call the PDD approximation. In VISAR, we had an approximation. There's also one in PDD. And that approximation is that your velocity changes slowly over some time scale that I'm going to call tau, where I want to do my analysis. If that's true, the optical signal during that region would be harmonic. So here's my interference equation. I'm saying, well, there's going to be a velocity here that's more or less fixed, and that velocity plays the role of a frequency. If I were to take a short time Fourier transform over that region, I'd get a power spectrum, and the peak of that power spectrum would tell me where what the Doppler shift is. So the way this works is if I take a little bit of signal, that's this black curve, I multiply by a digital window. This allows me to have the function go to 0 at the edges. I do some zero padding, and I pass this zero padded windowed signal into a FFT routine. You get a Fourier transform. Now the Fourier transform is actually complex valued and it has positive and negative frequency components. So usually what is done is you chop off the positive part, you add you sum the square of the real and imaginary parts, and you get these power spectrum. And those peaks tell you that there's a Doppler shift here and there's a Doppler shift here. So every single one of these slices of this image originates from this type of analysis. I took a chunk out, processed it, Fourier transformed it, and then I stored this part in my image. If you actually want a velocity history, you usually have to invoke some sort of region of interest. And this often requires some human intervention, where the spectrogram here, a person can look at that and say, oh, well, my interesting thing looks like this, so I will trace that out. And then what you do is at every time step of the image, I look for, like, say, where the peak is. Where's the peak location? I can do that by looking at center of mass or centroid. I can fit a Gaussian, whatever, and I write down that location. I subtract off the reference value as necessary to scale by half a wavelength, and I get something that looks like this. So in this test problem, I made up a step, a hold, and a ramp release. My history analysis is the black curve. And there's, it's not a bad fit. I mean, you do see that the rises are a little different, and that's an artifact of how big my FFTs are, how much data did I use in generating each spectrogram. That smears information this way. One of very famous scientists, Los Alamos, used to say that, the spectrograms don't lie, but histories sometimes do. And the reason is that there's a whole set of assumptions that go into making this spectrogram, what my FFT size was, what window I'm using, so on and so forth. But then you have to introduce a whole other set of assumptions to get to here. So sometimes people don't trust this. However, this is usually more helpful than that is, particularly if I'm looking at a wave profile measurement. So it's very important that we are able to pull out histories, hopefully without too many artifacts. So in PDV, there's a very obvious trade-off between time resolution and frequency uncertainty. Those of you who've taken quantum mechanics have probably heard of the uncertainty principle. And it's a similar principle applies here, that if I use a lot of data, a lot of signal, I have a very tiny frequency uncertainty, but I have poor time resolution. It's exactly the same logic that leads to the uncertainty principle in quantum mechanics. That is to say, the product of time and frequency width is fixed. Now, it turns out the uncertainty principle is true, but it's a little misleading. So here's an example of Fourier transforms of the similar data it's just been shifted for clarity, where I use more data and a little less data and a little less data. Clearly, I get more spreading, which is what the uncertainty principle measures, but I can tell you where the peak is to better than the width. Turns out the resolution actually scales as 1 over the 3/2 power instead of just 1 over tau. In fact, this is what the uncertainty of your beat frequency is. It depends only on the sample rate of your measurement, the amount of time data you use in your Fourier transform, the noise of the signal, and the amplitude of the signal. And you can explicitly show that this is the limiting resolution of a PDV. It turns out a similar limit applies to Visar, but the key difference there is that you have a physical delay. That's the etalon, the glass that you put in the Visar when you built it. In PDV, the time scale is set in software. So you can decide, do I want that to be 1 nanosecond or 100 nanoseconds? You can't go back on a Visar and say, build a new Visar. The data is what it is. But there is a similar scaling relationship in a Visar. So the limiting resolution in a PDV, I plotted here sort of characteristic resolutions for different levels of light return. This can be a little confusing if you're not used to these logarithmic scales. 0 dBm is 1 milliwatt. That's convention. So if I get 1 milliwatt of light back from my target, we call that 0 dBm. If I only get minus 10 dBm of light from my target, that's 0.1 milliwatts. Typically, we send plus 20 dBm, which is 100 milliwatts, and we have losses from 30 to 60 dB. So it puts us in this range of different return losses. And then based on the analysis timescale, you can figure out what the limiting velocity resolution is. And basically, this is really driven by the timescale. If I want nanosecond timescale resolutions, it is possible to get meter per second uncertainty with good light return. Now, if I'm larger than 100 nanoseconds, then sub-meter per second uncertainty is trivial. Now, there are some assumptions here we'll talk about later that the spectra are well separated. Let's just kind of give you a sense of how things operate for different timescales and different power levels. So I'm going to go through some PDV examples. Now, the first example, this is an impact experiment we did here at Sandia, where you've got a projectile and a gas gun. Gas is driving you from rest here to a few hundred meters per second. And we have a PDV measurement looking all the way down the barrel at the projectile itself. So this is probably, I don't know, maybe 4 meters distance when it starts. And it's slowly, because of the way this breech works, it's what's called a wraparound breech. The breech creeps forward very, very slowly until it gets past this O-ring, and then all the gas from around drives the projectile inward. And you actually can see that in the spectrogram, where your impact is maybe here at time 0, but as early as 80 milliseconds prior, you had this creeping of the projectile in its barrel very, very slowly. So about minus 40 milliseconds, I get a small kick, and then around 20 milliseconds, I get the main acceleration that actually takes me down the barrel. So you can see these tiny details in your PDV because I have such large FFTs. If I'm only carried about sub-millisecond time resolution, I've got massive Fourier transforms. When it comes time to impact, though, we have another PDV looking through an optical window at a sample that's being hit by this projectile. Well, here I get a reverberation on much shorter time scales, and the spectra are quite a bit wider. That's your uncertainty principle at play here, because I have to use much smaller. If each ring here is sort of 200 nanoseconds, I can't use microsecond FFTs that would wash out all of this data. So I use smaller Fourier transforms, I get broader spectra, but I can still resolve these fine details. We've also, you can use PdV in ramp wave measurements. So this is an example from our Thor machine. Thor is a electrical pulse power machine where we can tailor the drive very, very carefully. We had a summer student a few years ago who would use these ramp waves to drive compression in water. Excuse me. And the compression would actually cause the water to freeze, solidify, and you get a pullback signature here. That's actually what you're seeing, the transition from liquid water to I7, and you continue on compressing here. We've also used PdV extensively on Z to look at imploding cylinders. I think this is a copper cylinder with current flowing on the exterior surface, and it implodes on itself. Now we're talking velocities into several kilometers per second, until ultimately, if the current burns through, we start seeing some strange features, and then eventually the surface deteriorates because you have megamps of current flowing through. It's no longer a metal, it's a plasma, and we're not able to reflect very well off that plasma. Here's an example of extracting the velocity history, where this is a conventional PdV measurement. We had a plate impact on I think this is a copper sample being hit with an aluminum impactor, and so you get this ringing here. Here's a frequency shifted version of the same measurement. They were done simultaneously. And what we notice here, there's this baseline where here's where the rest state, I jump up and have my reverberation, but I still see this extended baseline. Using some clever signal processing, you're able to remove that baseline, and you can very precisely pick out the precursor. So see, the red is the PdV and the black is Visar on the same target. Very, very similar, even down at this tens of meter per second range. So yeah, this is usually what people want to look at, because you can easily compare it to your wave code and say, well, how does this model agree or disagree with my measurement? So let's compare the two diagnostics, Visar and PdV. What are the differences? Well, some of the major differences are sort of highlighted here. Visars tend to be open beam and or multi-mode fiber. PdV is almost exclusively single mode fiber. Visars usually visible light, almost always 532 these days. PdV is usually infrared in what's called the C band. This is where erbium amplifiers work in the telecom region. Now, these are not absolute. You can build a visible PdV, you can build an infrared Visar, but generally this is what you see. In a Visar, the maximum velocity is independent of bandwidth, whereas in a PdV, the maximum velocity depends specifically on bandwidth. That if I want to measure 10 kilometers per second, I need to have 13 gigahertz of bandwidth. In a Visar, that particular concern is irrelevant. In a Visar, your timescale is defined in hardware. In PdV, your timescale is defined in software. Visars are generally analyzed in the time domain. PdVs are usually analyzed in the frequency domain. The Visar is really optimized for single velocity measurements, one thing at a time. The thing can change, but you can't be more than one in the field of view. PdV can measure multiple simultaneous velocities. For a lot of applications, makes PdV preferable, particularly if you're studying things like ejecta or your non-ideal measurements. Having said that, PdV analysis can be extremely tricky. I've got some examples here taken from, these are actually all from Z, where there's really only one physical velocity of interest, but the spectrogram is rich with features. In this top spectrogram, we see this line here, which I have labeled C. This is the actual downshifted measurement of interest. It's supposed to go down and bounce like this. However, we see an extended baseline here. This is light that isn't Doppler shifted. It's usually reflected in the probe or somewhere. It's still in the measurement. We actually have kind of an artifact of a conventional PdV signal here, which crosses the thing of interest. So that's a lot of fun. You can also get electrical harmonics. So in this lower plot, the dashed line shows you the thing we care about. But then we often see, if this was, say, just under 2 gigahertz, we see copies of that thing at twice, 3 times, 4 times. That's a nonlinear effect either in the detector or in the acquisition. You can also see optical harmonics where you pick up light, multiple Doppler shifts, but they're on a common offset. And sometimes separating those can be interesting. One of the real frustrating things about these overlapping features is you get spectrum modulations. So for example, in this feature up here, when it's overlapping with baseline, you see these light dark regions. This is not actually a change in optical reflectance. It's the overlap of two very closely spaced frequencies. And as you separate, you can see how the frequency gets higher and higher and then eventually vanishes. But then it picks up here as these two things cross. Now, you might ask, well, why is this one beating in and out? And it's because mathematically, all frequencies have, all real sinusoids have a real and imaginary frequency. So although I've got a Doppler shift here, I also have a negative Doppler shift, and those are overlapping. You can actually tell because this thing is at twice the frequency of that. If you look at those modulations, this one is increasing twice because you're getting a splitting where the offset is in both directions, and here it's only one direction. So sometimes pulling data out of PDV is not easy if the spectrogram is rich. There are lots of other PDV challenges. One of the big ones is dynamic speckle. So it turns out the mixture of coherent laser and rough surface is not always in your advantage. Basically, all light come from the target. If it has the same frequency but different paths, you get coherent addition. And what can happen is your signal can look something like this. If you zoom into it, so this is a long time scale, and then say this is just 300 nanoseconds here at the beginning, the whole thing is totally coherent, but you get these dead spots where it just happens you're in a dark part of the speckle, or the dark speckle is on the fiber, and you get dropouts. And then they're totally random. The only way you can really mitigate them is to have multiple redundant probes that are sufficiently far apart so that their speckle is independent, and then it's a statistics game. If you have 3 independent measurements, it's unlikely that all 3 die simultaneously. There are also some problems with just the fiber itself. If you're a 9-micron core, you can't fit as much power without risking burning as you could in a multimode fiber. PDV also suffers from Brouillon scattering if you're sending too much light over too much fiber. You say, well, what's too much? Turns out 100 milliwatts of fiber, if you have 100 milliwatts of power, over 100 meters of fiber, can give you artifacts that you would not see had at lower power or shorter fiber runs. So that's kind of a challenge too. I often get asked which is better. Well, VISAR is technically more sensitive, but it is more complicated than PDV. So the sensitivity comes about from the shorter wavelength and the fact that you've got multiple signals, and that is that you reduce noise because the noise is uncorrelated. Having said that, the open beam alignments are challenging, and the multiple signals means you need more digitizer channels. So yeah, those channels might be cheaper. It means, your digitizer might be cheaper by the channel, but if you need 2 digitizers per VISAR measurement, you may not have saved any money. But the truth is both VISAR and PDV have their merits. If you're looking for wave profiles, these are windowed samples, one-dimensional compression, use what you have. However, you probably want PDV for everything else: detonation, ejecta measurements, anything that isn't just a simple 1D sample, windowed sample. If you were building a new facility or particularly a university, it may not make sense to build a VISAR if your velocities are always under 15 kilometers per second. I sort of pick that arbitrarily based on what's off-the-shelf digitizers and other equipment. If you're going to be much faster than 15 kilometers per second, which is usually limited to a handful of facilities in the world, VISAR still makes a lot of sense there. Your digitizer really dominates the upfront cost of a PDV. So as a young faculty member, you got to understand, that could be more than 100K up front. But once you've built it, the operation and maintenance of a PDV is much easier than it is for a VISAR. It's usually something you can train a student to do with very low risk that they're going to destroy something. So I was going to summarize here that velocimetry is really a core diagnostic for dynamic compression. Virtually every experiment you'll see will have a VISAR or a PDV on it. We do that because those measurements can be directly tied to jump conditions and into wave simulations. Historical data is based on a huge chunk of that is just arrival time measurements. Velocity is the shock tables. I don't think any of those measurements are based on anything other than velocity. Optical velocimetry these days is now usually based on the Doppler shift. In a VISAR, you encode that shift as a phase on a set of quadrature signals. You need at least 3 or 4 measurements, but you don't need to have high bandwidth, but you also cannot tolerate more than one velocity at a time. A PDV encodes that shift as beat frequency changes, so you only need one signal, possibly high bandwidth, however. You can, however, handle multiple velocities. Overlapping features can be challenging to analyze, although, to be fair, sometimes those measurements wouldn't have given a useful visor measurement anyway. So, it's something to consider. I've assigned 2 exercises for people to consider this week. The first one is mostly a computational exercise. Suppose that you have a 1550 nanometer PDV and need to measure something moving at 1 kilometer per second, 1,000 meters per second. What is the minimum bandwidth we need to track that motion? That's the first part. The second part is, for the same velocity, what is the eddy-long delay needed for 10 fringes in a 532 nanometer visor? So this is sort of how would you set up a measurement to track up to 1 kilometer per second, excuse me. The bonus question here, for those who are very motivated, is to figure out the limiting velocity resolution for the PDV measurement at 10% noise, 80 gigasamples per second sampling, and 10 nanosecond FFTs. And then how does this compare to a visor? The hint here is that Lynn Barker had a rule of thumb that in a visor, your limiting resolution is 1 to 2% of the French constant, which you will need to derive in this part of exercise 1. So that's the first exercise. The second exercise is a more conceptual task where you say, suppose I have a wedged projectile moving from left to right at a velocity v. If I were sitting at point A, what velocity would a visor measure? And what about a PDV at that point? Now, if I were to turn around and say I'm at point B, and my projectile is going by from left to right, I'm seeing a spot on the target move towards me, because when the projectile starts, I hit the tip and moves closer and closer. What velocity would I see in a visor and PDV at this location? And does the distinction that visor is a velocity interferometer and PDV a displacement interferometer play any role here? So this is much more of a conceptual question. I will warn you, this had caused many arguments about 10 years ago. It's not as obvious as you think it might be. So think through this one carefully. So the other one's more of a calculator exercise. And I think with that, I'll stop. Let's see, we're right just under an hour. I can take some questions and stay on chat with as long as people would like.
Thank you very much, Dan, for this great talk. I am going to suggest that we do questions the same way that we've done them before. So basically just type them into your chat box. I'll read them out for everybody to hear, and so that they get recorded. And Dan, you can take a crack at them. You can also read them in the chat box. Sound good? All right. So we have one question here already. Great talk. Thank you. This is from Felipe Gonzalez. I still don't understand the concept of free surface velocity in visor. Does the entire specimen move after the shockwave hits its free surface at a certain velocity? Or is it just a bulge that forms in the specimen's free surface that moves at u sub fs? If this is the case, does sputtering occur? Does the free surface stop moving? How far does the surface move?
Okay, well, there's a lot to unpack in that question, but let me, see if I've got a picture here. It depends on timescales that you're talking about, but when where's the, okay. With this, yeah, I'm still sharing, okay. So like, for example, in Lynn Barker's diagram here, he's got the specimen. How this shock works depends a lot on the projectile and the specimen. So for the sake of example, let's just suppose that these were the same material, like aluminum or copper, whatever. They're symmetric. So on impact, you generate your shock wave, which has a non-zero particle velocity behind it. When the shock breaks out here, you get a release velocity, which to a first approximation is half of the immaterial velocity. And so that surface is kicking off faster than the particle velocity was in the behind the shock front. And then you have a release wave that travels back. What happens thereafter? So you do get, it might look like a bulge at first because the rest of the specimen is compressed, and this release is letting the pressure out. So it's bulging. It's not necessarily larger than it was originally, but it is larger than it was in the fully compressed state. Now, what happens after that really depends on the relative impedances here. If it's symmetric, if they're the same material, you actually launch this, and at least for low compressions, you you get some ringing here that eventually dies out, but eventually the projected specimen is traveling at the same velocity as the projectile was, and if it's symmetric. But higher impedance, low impedance gives you different things. Do they stick together? But yeah, you actually can get this to move out. Now, all kinds of other things can happen too. I think some of the previous speakers have talked about SPAL, where if you get a release from one side, crossing a release on the other side, you can form a tension, and that can form voids in the interior. And that is often measured with stuff like Visar. You can have eject. I mean, this surface we show is this perfect flat interface, but if there's structure in here, peaks, valleys, those locally can create jets that spew material out as well. So a whole host of things can happen depending on the experiment. Hopefully, I don't know if I answered exactly what you were looking for, but
Felipe, feel free to follow up if you want to unmute yourself.
Okay, thank you. Yeah, actually, I want to understand what do you mean usually when I read papers on that use Visar. What do they mean when they measure this surface velocity? For how long is it measured? How long does it last? That is for surface moving. And I was always confused whether the whole specimen is moving or you're measuring the velocity of the bulge only.
We're measuring. So we're measuring the velocity of that. I guess you can call it a bulge. I mean, look at the timescales here on Lynn Barker's paper. This is in microseconds. So he's measuring from 0.16 to 0.36. This is 200 nanoseconds is all we're measuring that free surface velocity for. And when they say free surface, they're just distinguishing it from a windowed target. Because if you have a windowed, if there were an optical window there, that changes the state and also the interpretation. There's some window corrections I did not get a chance to talk about today. But yeah, it's only measured for a short amount of time before edge waves come in. So you're still talking one-dimensional uniaxial strain assumption.
Okay, thank you.
I have a quick question. Rather than typing it into the chat box, I'll just ask it out loud. So you talked about measurements basically under the assumption that the entire surface was moving at a single velocity, not at multiple velocities.
Yes.
And at the same time, you also, mentioned these interesting things about how the surface finish would change after a shock, for example, during microjetting.
Yes.
And, I wonder if people have never been able to resolve multiple velocities along a single surface, how do they ever come to conclude that things like microjetting is occurring?
Well, so I'm not an expert at when it comes ejecta. That's not, but I know some people, Los Alamos, who have studied this for years, and my impression is that, so windowed targets tend to be pretty good. So if I slap a lithium fluoride window or a sapphire window on a material, and as long as everything's relatively flat, I will see a very clean Visar or PDV measurement. If you're in a free surface configuration and you say diamond turn a metal like that, you're often still generally okay as long as you're well below the melt threshold of shock melting. But it's as you start like intentionally roughening the surface or putting grooves or things that really enhance the production of microjets, that's when you start to see problems with the Visar. And honestly, the ejecta community was one of the early adopters for PDV because they had a long experience of their Visars just failing. That you have perfect optical setup beforehand, shock would come through, then you got this ejecta spray, which you could say resolve with radiography, or you could detect by putting foils at various locations and know that things were happening. But your Visar signals you'd lose all contrast, and you couldn't get any data out of it.
Would it be correct to say though that the existence of these jets is really an inference from ejecta that have been collected afterwards, rather than through some time resolved measurement?
Well, okay, so yeah, I mean, the traditional way you use what they call in a safe foil, where ejecta mass coming off the surface would be accumulated onto a foil, and then you'd measure the velocity of the foil. But in PDV, you can see distributions of velocity um, straight off in the spectrogram. So that's not something that this part of Sandia does very much of, but there's a huge area in Los Alamos and at Livermore of ejecta studies. That was something Dave Holtkamp had really done a lot of, and you could see distributions of velocities directly.
Okay, we have a question from Travis Volts. Have there been any attempts to create a line PDV system, or to make such measurements? Would you just use an array of individual PDV probes?
People have talked about line PDV for years, and I mean, there's no fundamental reason you can't do it. I mean, one of the big differences between line PDV and line visors typically open beam imaged onto a street camera. Street cameras do not work in the 1550 nanometer wavelength range, but you can imagine having an array of optical fibers, and in fact, they're commercially available. You can get 16, 32, 64 fibers in it. You want them in a line, do you want them in a square, however you want them arranged, imaging those onto a target. The challenge with line PDV is more of a data management and recording capability. So it's, can you afford enough digitizer channels, or can you do what's called multiplexing? There are ways of encoding more than one PDV on a common digitizer channel, because digitizers are expensive. You don't necessarily want to have 256 digitizer channels because you break the bank. Now, it's not line PDV, but the folks in Las Vegas and Nevada they do these pin dome experiments where you're imploding hemispheres. And I think the record now is 256 points. So they're not in a line, they're all over in different directions. And they heavily time multiplex the signals so that you don't have to buy as many digitizers. So yes, I mean, I don't know of one to specifically recreate line visor, but spatially resolved PDV is definitely doable. It's more of an economics and engineering question.
Okay. Any other questions? Here we go. Tom Nizolik. What would be a typical spot size for PDV? What would be the minimum that is highest spatial resolution?
Okay, well, if we start from just the single mode fiber, SMF28, that's a particular blend that's used for this wavelength. The core size is sort of 9-10 microns. So if you were imaging, theoretically, each spot would be, comparable size, sort of 10-ish microns. Now the trick is in standard imaging, you wouldn't be able to get two fibers more than 125 microns apart, because that's the cladding that sits around the fiber. So you can imagine having 10 micron spots every 125 microns. There are some ways of packing denser than that. You might be able to get sort of 80 microns. There are ways of even doing 50 microns, but you're sort of talking a specialty fiber, just getting the cores close together. Now, having said that, you could always start with a larger array and then image it down optically. But in standard PDV, your space between points is 125 microns.
Any other questions? If not, then I wanted to thank Dan once again and invite all of you to join us on Thursday at the usual review session time to go over the two exercises that Dan provided at the end of his slides. I'll send out the slides, of course, as usual, to all of the registrants after the lecture. So thank you very much and have a great day.